So my job is to try to get us to a level set so that we know the basics, the big picture of what Vulkan is trying to accomplish and kind of how it's shaped. And that sets the stage and provides the context for the other guys who are going to speak later. So what's Vulkan? Its ambition, first, is to be for the next 20 years what OpenGL was for the last 25 years. That is to say, it's supposed to be the de facto industry standard for cross-platform access to GPUs. It is logically connected. It's the same people doing it. It was all the OpenGL and ES guys. And the concepts, the model of what a GPU is, are similar. But it's, on the other hand, a complete design from the ground up redesign. It's not vaporware and it's not far future, it's here. We released the spec really only in February, so it hasn't been around for long. But the day that it was released, there were drivers available for Windows, for Linux, and by now, all three of the big desktop vendors, AMD, NVIDIA, and Intel, have drivers. Sadly, they don't support, Intel does not support Vulkan on this laptop, except in Windows 10, which I'm not going there. So I'm Vulkanless currently, but my time is coming. That's desktop. It is also shipping in the Galaxy S7 from Samsung, which Alon's probably got in his pocket, and would be happy to show you, I'm sure. That's on 2 different GPUs, because those devices span multiple hardware platforms. Google is heavily involved and is pushing Vulkan for Android. They've announced that it will be exposed and supported in Android N, which is coming real soon. Finally, it's really different. As I said, it inherits some stuff from GL, but the basic philosophy of the API design is fundamentally different. That implies that the design of your application is just going to have to be fundamentally different to account for that. And that's mostly why we're here talking about this. So when I say something like that, it may sound scary. You might say, why are you putting us through this agony? Well, if you're a GL user, you probably know. GL had certain issues and accumulated over time, and it began to get to the point where the tree was about to fall over. So if you go back to, well, as I say, this is a problem that built up over 2 decades, but really began to come to a head in the early teens, 2013, 14. And in 2014, we had guys who are really good friends and proponents of OpenGL writing blogs like this, saying OpenGL is broken. Its current state is incredibly frustrating. It is driving, here are 15 things about GL that drive me crazy. And as I said, this is what our friends were saying. The DX fans were saying was even less polite. But we appreciate it, and we were actually listening. So I'll give you my own list. Rich Geldrich's blog is great for a more detailed one. For my money, the fundamental problem was that the programming model was stuck back in 1992 and had not evolved the way the hardware had evolved. So there was a huge mismatch between the abstraction the API presented, like it pretended everything was synchronous, right? You give the GPU a command, it does it, and then you give it another command, and it does that. Of course, that's not true. You give it lists of things, and it goes off and works asynchronously, and eventually gets it. GL didn't expose that. It was all hidden from you, and it was hidden by lots of driver magic. That driver magic had a cost. It loaded down the CPU a lot to preserve that illusion. And in addition, the driver was, the CPU was doing lots of work to check every command you give it and make sure it makes sense, to compare and make sure there's nothing inconsistent, and to report errors to you nicely if you did something wrong. Also, to detect, for example, if I start drawing something and using a texture, and then I immediately say that I want to change the pixels in the texture, the driver was responsible in GL for saying, well, I see that you're trying to do that, but I'm not actually finished with this, so I'll either stall you and change the texture later, or I'll make a shadow copy and change the shadow copy. And so there would be all this stuff happening, some of which was very expensive. Go copying a 4K by 4K texture, it takes a while. And so lots of CPU work. The complexity and the load of this led to drivers getting very big and very complicated, which sadly meant that few of them had bugs. Not many, but a few. Not ours, certainly. And they also, let's add to that, that in order to give you good performance on key commercial applications, the driver writers were also putting in magic to move work around and try to optimize what you were telling it to do for what the application was asking for the hardware that it was running on. The result of that was that it was very hard to predict what was going to be cheap, what was going to be expensive. You were kind of in a position, it's like working with certain optimizing compilers, trying to trick the driver or hint to the driver what you wanted it to do. And it certainly wasn't going to tell you. It was kind of a mess. Possibly the most important thing, gee, I have a pointer here, it's kind of poor. No, I hate it. Possibly the worst thing in terms of getting behind the curve technologically was that the model is fundamentally single-threaded. Yes, there's a threading model in GL, and you can have, make contexts current to multiple threads. That in 3 bucks will get you a cup of coffee. It's pretty useless. You really can't make effective use of multiple threads to do driver work in GL. The cruft issue, I won't go there. There's, we've all got our favorite examples, but the API was designed in 1990 and it looks like it. So the goal of Vulkan when we kicked this project off was to try to fix these problems. We actually started before the community got really antsy. We started looking at this in 2012 and did some preliminary design work, but it wasn't a huge priority for us. We didn't really get the urgency of the problem, and we didn't make a lot of progress. We did get some good ideas formulated. Does the sound quality sound really weird in here? I'm hearing this buzzy. No, you're happy?
So far, the colors.
Okay.
Fine.
All right. It sounds like I've had an echo or something. Anyway, so we started some work in 2012. Didn't really make a whole lot of progress. We saw the blogs that came out in early 2014. We reacted to that, and in particular, it was awesome. In 2014, a bunch of the senior ISVs in the community, Unity, Epic, EA, Blizzard, came to Cronus and said, look, you really have a problem. We want you to solve it. We will help. And so we got really the project rolling. And then the biggest boost we got was when they donated the IP and Mantle, our proprietary low-level API, for us to use as a starting point. Committee processes are not really good at coming up with stuff from scratch. They kind of need to start with an artifact that is okay, and they're very good at making it better. Ensues a whole bunch of work. This is the class photo from our last face-to-face meeting. You can't see it terribly well, can you? There's actually a whole bunch of the people who are speaking to you today are in this picture. There's me. I'm wrong. So anyway, this is not the whole team, but this is a lot of it. Leading to release in February. As I said, with a pretty complete ecosystem behind it and pretty ready for prime time. So I guess what's happened since then, I guess I would say, is that from a Cronus perspective, the adoption of Vulkan that we've seen is orders of magnitude faster than anything we've seen for a previous API. The lead time from OpenGLES 2 spec delivered to fielded was 4 years. Vulkan, GL 4.5 is still not supported on lots of desktop hardware. Vulkan is moving to the market at a rate we've never seen before. That's cool. So I've kind of talked about, that was the political background and the sort of business person or committee person view. I'm going to talk a little bit technical now. I'm not going to show you any code. The other guys will do more of that than me wanted. But I am going to say, what is Vulkan shaped like? What is it? How is it organized? So this is Vulkan in one slide. Your application starts by creating an instance. Everybody probably knows that in a serious GL system, certainly on Windows, when you start your application, you don't start GL. You start some helper like Wiggle or EGL or some helper library that helps you create a context. And then you build a table of function pointers, and there's this all this snarl, trampoline context, all that good stuff. Anyway, if not, I'm not going to explain it. It's not pretty. But that all depends on these external APIs like EGL. Vulkan brings everything inside. So the instance that you create initially is not a driver. It's an interface to a loader. So you create the instance, you ask it what GPUs it has available. The politically correct term is physical device, but for GPUs. So you say, what GPUs have you got? You query their properties, you decide which one you want to use, or multiple if you want to use more than one. And then you ask the instance to create a logical device. And you do everything else you do is relative to a logical device. So what kinds of things can you do from it? Well, mostly you create objects. So if you're doing graphics, you're certainly going to want to create some textures, memory buffers, vertex buffers, etc. In GL, when you call, like, what's the new way to create a texture? Text storage, 2D, you get a texture. It's ready to go. It's got a size, pixel format, memory, everything. In Vulkan, you get, when you create a texture, it's got a size and it's got a pixel format, but it has no memory to put the pixels in. That's because in Vulkan, your application owns and allocates GPU memory, not the driver. So you need to allocate some memory. And then, if you're being smart, you allocate one big chunk, and then you bind pieces of that memory to all of the objects that you've created. And you can play games with aliasing if you know what you're doing, and you don't have to. Lots of stuff you can do there. At some point, you'll need to create a queue. That's the place where you're going to hand work to the GPU to execute. It's a queue because, of course, you want to stack stuff up and keep it busy. And the most fun part, where you'll spend almost all of the time in your application that's spent in Vulkan, will be spent creating command buffers to submit. Submit is really fast, really lightweight. Command buffer work is expensive and hard and requires driver efforts. And like I say, it's where you're going to spend most of your time. So that's Vulkan in one slide. You may be saying, well, I can see that the API is going to look different from GL, but it's not actually logically that different. It's not complicated, is it? Not yet. But actually, there is more to it. Okay, so this is the big picture. That's the architecture of Vulkan, kind of. It's a little bit oversimplified, as you'll see. Because most of what you do is involved with, most of the work you do is command buffer construction. I want to talk a little bit more about that. So it's actually Vulkan in 2 slides. So what's a command buffer? It's a list of work that you want the GPU to perform for you. So what you do is you create one and then you record stuff into it by making function calls that put stuff into the command buffer. And there are lots of different things you might put in there. But let's assume typical graphics, what you really want to do is draw something. So you would start by inserting a pipeline. A pipeline is a bag of state, so it contains things like your blend mode. And all the other, you remember in OpenGL, you make all these individual function calls to set bits of state on the global context. In Vulkan, you set them in a pipeline. You bind that pipeline object to a command buffer. And after I'm done talking, Michael Worcester in the back of the room is going to go into considerable detail about pipelines and command buffers. One of the things you will stick in the pipeline is the shaders that you're
that the GPU is going to execute for you for each pipeline stage. It doesn't show up here. I'm not going to stop. So you will stick shaders into your pipeline. The shaders are not GLSL anymore. They're not a high-level language. They're written in a portable, that is cross-device binary format called SPIRV. And after Michael talks, Neil and Hans Christian are going to talk about what SPIRV is, how it works, and some of the tools that we have available to manipulate it. So you've bound a pipeline, so you've got state for a draw call. You also need to supply resources, textures, etc. And the way you do that is by binding descriptor sets. So a descriptor set is basically just a table of references to resources, those textures and buffers that you created earlier. And the way your shader accesses a particular texture is by supplying an index into a descriptor set. So that's pretty straightforward. Jesse Barker in the back of the room also is going to talk about descriptor sets after Neil and Hans Christian. So finally, you can do a draw call. Yay! And you can do it all again. And Vulkan is really, really good at doing draw calls fast. So we expect you're going to do lots and lots and lots of this stuff. There are additional complexities, I'm sorry to say. Sequence of, this is a lie, and Andrew will explain why. But the oversimplified view is that a group of successive draw calls that are directed to a single frame buffer forms a render pass. And it's formally defined. You say begin render pass, draw, 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 and render pass. There's, like I said, that's not strictly true, but think of it, pretend it's true for now. It's the render pass construct that is largely responsible for Vulkan being great for tile-based architectures that we use in mobile, as well as for desktop architectures. Doesn't help them as much, but it does help them. There's a lot to know about render passes, and Barrett from Samsung will talk about them later. So this all sounds pretty reasonable, and if you look at this, you put these commands into the command buffer in an order, and you might think they execute in order, but no. They're actually very briefly constrained as far as execution order. And furthermore, when you stick these command buffers onto a queue, their order is also quite weakly constrained. That's to maximize opportunities for parallelism. So if you do have dependencies between commands in the command buffer or between operations submitted to a queue, you have to tell Vulkan about that. And you do that by inserting synchronization tokens. There are some that you stick in the command buffer, there are others that you stick on the queues. And Tobias Hector from Imagination will talk about those. And there is other stuff that can go in there, copy operations. Multi-sample resolve is expressed by doing an operation in the command buffer. And so on. But this is kind of the big picture, Vulkan in a nutshell, or two nutshells. So, how am I doing on time? Not too bad. That was the Vulkan 101 really. Most of what I'm going to spend the rest of my time on is justifying that claim I made earlier that Vulkan is really different. You can see that this is, obviously it is different from GL, but it's not obvious from what I've said so far just how different it is. So I'm going to talk about a couple of the ways in which it's maybe a bigger deal than it looks like. So I said on slide 1 that Vulkan was based on a different philosophy from GL. And we thought about this quite a bit for about in the early days of the project. When we started with Mantle was explicitly a low-level API. You could see the bones of the GPU kind of under the skin of the API. When we tried to extend that philosophy to handle GPUs from 8 different vendors, including some that were tile-based and some that were not, it became clear that we weren't going to be able to be low level in that sense. And we eventually decided we didn't really want to. We don't really care about low level. The principle we settled on, what we said was the organizing principle, was explicitness. That is, that it boils down to getting rid of the magic, getting rid of the driver trying to outthink the application. The way I think of this is that we've rewritten the contract between the driver and the application. So what we expect you, the application writer, assuming you are one, to do is to tell the driver what you're going to do and to tell us in detail. So for example, in GL, you can create a texture, and then later on, you can decide, hey, I think I'll render to this. In Vulkan, when you create something, you're going to say, this texture is just a texture, give me just a texture. This texture is going to be a depth attachment in a frame buffer, and by the way, I'm also going to sample it. So you have to specify all the uses you intend to make of something early. This insufficient detail that I put on the slide has a corollary, which is that Vulkan is very verbose. You're going to have to say a lot more stuff that you could have just implied in GL. So that's a cost. There is a trade-off for it. There is a benefit, which I'll get to. So you're going to have to tell Vulkan, you commit to telling Vulkan what you're going to do in a lot of detail. You also have to tell it when the driver needs to know. So that the driver doesn't have to guess or defer work and do it later at a time when you didn't expect it to. Because Vulkan, well, sorry, I'm getting ahead of myself. When the driver needs to know it, I should warn you, is earlier than you think. To explain why you kind of have to be a driver writer or spend some time looking around in the guts of a driver. But you're going to have to give the driver a lot of information, and you're going to have to give it earlier than you expected to. This is at the heart of my statement that you're going to have to design your applications differently. In order for you to tell the driver this information early, you're going to have to know it early. And if you've architected and you're used to thinking in a DX11 or GL style, you may not be prepared to do that initially until you kind of get your head around it. So it is going to have an impact. So there's this heavy burden that we place on you, the app writer. What do you get back as a reward for that? In return, the driver promises to do exactly what you told it to, and exactly when you told it to. This has a big impact on real-time applications. I mean, you're probably familiar, if you've tried to write a game, with getting frame hitches where the driver, very late in the game, in the middle of your render loop, suddenly decides, gee, I think I need to recompile this shader, and it forks off the GLSL compiler, and your frame just stops for a second. That's bad. Vulkan promises not to do that. We will compile that shader when you give it to us, when you build the pipeline, and we will not touch it again. Right, and then finally, this happens not only when you ask for it, but very quickly. We get rid of the magic. So we're kind of doing it. This is a random grab bag of things about Vulkan that are different. I talked about the loader, which builds the table of function pointers that is appropriate for the device you have asked the instance to give you access to. That's basically like an ICD loader, or I'm sure you've seen these in other applications. Window system binding is also somewhat built in. Once we've got the mechanism for having this loader part of Vulkan, we can use that for other purposes. And a really cool purpose that we use that for is what we call the layer system. So what this is that the loader, since the loader is building a table of pointers to all the functions in Vulkan, it can also stick in shims. I'm carrying.
Carry on.
Okay. Right, the loader can shim the API and stick in functions that intercept what you're doing and make changes to it. The canonical thing to do with that kind of, if you've used API trace, for example, that's a shim layer. RenderDoc has capabilities like that built in. What that lets you do is, for example, you might find it useful in debugging your application to be able to capture a trace of all the GL calls with all the arguments that your application has made. You can do that using external tools in GL. Vulkan has this built in through the instance. You can just turn on a trace layer, enable it, and the loader will silently put intercepts on every function in the API, and those intercepts will, when you call that function, will record in a log file, etc., that you've done that and what the arguments were, and then pass control to the underlying function, and it all happens seamlessly and silently. When you're done with this and you don't need it anymore, you just disable the layer. It's gone. Extensions are also handled partly through the loader. The one thing I wanted to say that's cool and different about Vulkan is that we're in GL. It's really easy to use an extension by accident. You know, you can query what extensions are supported, and you should, but lots of people don't. And so you end up with code that isn't portable because it requires extensions that were on the implementation you developed on, but not on the implementations you're shipping on, and you get bug reports, and it's horrible. Vulkan requires you to enable extensions explicitly. You say, I'm going to use this. If you don't say you're going to use it, it's not there. Or rather, what you will get is undefined behavior. So that kind of prevents you from getting into that bind. Multithreading. One of the most important things that we were trying to accomplish in Vulkan was to be able to use multiple cores to split CPU driver work across multiple cores. And there's a bunch of design principles that we followed that make that possible. Vulkan has no notion of a thread owning something. Threads do not own anything, so there's no thread local storage. There's no notion of binding a context to a thread, etc. Any thread can see any object. Any thread is welcome to touch any object as far as Vulkan is concerned. You have to decide whether it's safe to do so. We give you the rules, and you decide and do the synchronization. The term we use in the spec for most of the objects in Vulkan is, or most of the operations on objects is externally synchronized. When we say, for example, putting things into command buffers is externally synchronized, what that means is it is not safe for two threads to try to put commands into the same command buffer at the same time. If you do, terribly bad things may happen. We expect you to synchronize around it. It's fine for two threads to do it, but you'd better make sure that no two of them are actually in the act concurrently of modifying the object. So that applies to command buffers, applies to queues. It's fine for multiple threads to submit to a queue as long as they don't try to do it at the same time. If they do, things are likely to explode. The application is also responsible for object lifetimes. If my thread deletes a command buffer or say a texture while another thread is reading it, terrible things will happen. That applies to the GPU as well. When it's part of this explicit control contract. When you say delete an object, it gets deleted then, not later. And so you are responsible for making sure that you don't delete something while the GPU is using it. It does help that compared to GL, almost all the key objects in Vulkan are immutable. Not command buffers, obviously, that would be not the point. But textures are immutable. The format isn't going to change. The size isn't going to change. Concurrent read access is fine. There's clearly no problem doing that. The exception to the general idea here is we don't want a Vulkan driver to be blocking ever. If you're trying to write a real-time application and you make a Vulkan call and it blocks, you've lost control. The operating system may not schedule your thread again for 10 milliseconds. So Vulkan tries very, very hard not to stall. And if it is going to stall, it's going to tell you where. It's going to stall in allocation, because that's one of the few places where you do global stuff, or object creation. So those may have, or the driver is expected to protect those operations and make sure that you don't get corruption through multiple threads trying to allocate memory, for example, at the same time. However, we also don't want you to be in the position of getting bottlenecked because your allocation calls are colliding and hitting operating system semaphores. The way we do that is that in these situations where you are, for example, allocating memory or allocating descriptor sets or command buffer memory, you allocate not from the global system but from a pool. So you create, for example, for descriptor sets, rather than just allocating them globally, you allocate descriptor pools. That could block, but you're going to do it at the beginning of the time. You give a descriptor pool to each thread that's going to do descriptor set allocation. And those objects are externally synchronized. So your threads can allocate descriptor sets from their private pools very quickly. They will not block. And it's only a problem if you accidentally give the same pool to two different threads and then you get something bad happen. Error handling, again, a philosophical change. Vulkan is optimized. Vulkan assumes you know what you're doing and is optimized for correct applications. If your application is correct, we don't want you to have to pay the price of having the driver check every argument when they're already correct. So we don't do any error checking to speak of. In the spec, every function and every table is accompanied with a big block of gray text, which says validity constraints or valid usage, something like that. And it lists all the rules that the arguments must satisfy. It's very mechanical and easy to read. You don't have to hunt through the spec to find it. It's all right there. So you need to follow those rules. If you don't follow those rules, you get undefined behavior, possibly including core dumping. So you want to be careful about that. So that's one class of errors, is invalid usage. The other big class of errors would be violating the concurrent access constraints that I talked about earlier. That also obviously can lead to bad results. The only errors Vulkan does check for are the ones that you cannot detect by carefully reading your code. So all these valid usage constraints, you can read your code and figure out whether you follow the rules or not. You can't detect out of memory because you don't, that's the operating system's business. You can't detect that the user killed the window that you were rendering to. So you have a device lost situation. Vulkan does check those and does report them. Of course, you have the small problem that you need to write your application and debug it. And you're going to make mistakes, and you're going to violate usage constraints and dependencies. That's where the layer system comes in. The really cool thing about the layer system is we have a fairly large collection of layers that you can turn on when you're developing. So they'll cost you something. And they will do things like, there is one which will check for invalid usage and report any errors you make through a callback or through a log. We have another layer which will check for illegal concurrent access. If two functions try to do write access to the same thing at the same time and break a concurrency constraint, we can catch those and report them. So you pay this price while you're developing, but once you're sure your application is correct, you turn them all off and there's no cost. We're almost at the end here. The last thing I want to talk about in terms of different philosophy. Kronos has been around for a long time. The Art's been around for even longer, and have sometimes presented, at least developers tell us, it looks to them like this. Kurt Akeley goes up on the mountain and receives stone tablets with GL cards into them, and comes down and here it is, and you don't question it, and it's all mysterious and magical. That's not a helpful attitude for Kronos to take. We didn't mean to project that, but it somehow came to us. With Vulkan, we're trying very explicitly to be more community-facing, more responsive. It is certainly the case that ISV input, as I described earlier, drove many of the key API design decisions. We also worked quite hard to consult with a larger population of developers during the design, their feedback. We've also made a strong commitment to open source. The loader that I described earlier is part of a driver, but it is available on open source and you can bypass it. All the layers that I talked about, the API for creating layers is exposed, and all of the layers that Cronus has developed or that Cronus members have developed are available on GitHub. If you find that the validation constraints aren't being checked or that you're hitting a validation problem that a layer should have caught and didn't, you can make a pull request and we will take it in. The compiler for SpearBee is open source. There is a validator that is, you can submit your SpearBee to a program which will tell you whether it's syntactically correct if you're writing your own compiler. Conformance tests and even the specification is available on GitHub. And we do our best to process the bugs that come in. A lot of bugs are coming in and they're very useful, very helpful to us. So we hope you'll take advantage of that. And forgive us when it takes us some time to respond. I think, oh yes, I do have one more slide. Should you use Vulkan? Only you can decide. There are definitely trade-offs and there are challenges. It's a difficult API, it's very verbose, it's very complex. It has sharp edges. We try to provide tools to help you not cut yourself, but there are challenges and it's a big learning curve. On the other hand, it is the wave of the future, and clearly is going to, we believe, is going to take over the world. You get much lower driver overhead, even on a single threaded CPU, and you can spread that driver overhead over multiple threads, which is cool. You get, in consequence of the fact that driver overhead is low, you can get pretty amazing draw call rates out of it compared to GL. You get more performance predictability. It's not going to be perfect. We're trying to drive it in that direction. And it's mobile friendly. It's probably even more important in mobile than it is on desktop, where we have power constraints. Reducing the CPU overhead reduces power, and that's really important. And the fact that you can, you have a much more coherent and clear way to talk to tile-based GPU architectures is also a big win. So there's reasons you might want to worry about it, and there's reasons you might want to do it today. Remember also the realities. Vulkan is penetrating the market quickly, but it's not on every device today. It won't run on this laptop. Probably, at least some of you also have laptops that can't run it, phones that can't run it. It is going to take time to penetrate. That means that you will still have to have a path if you're doing a big cross-platform application. You're still going to have to support the legacy APIs for quite a while. So I hope you will move to Vulkan, but you have to be prepared. Basically, what it comes down to, Hans Christian's going to talk about this, but because the Vulkan has these architectural constraints, what you're probably going to end up doing is wanting to design for Vulkan and implement a Vulkan path, but also then port that to GL. That's a relatively easy port. Port from GL to Vulkan is harder. How am I on time? I've got
3 minutes.
3 minutes.
Questions?
Anybody want to try a question now, or do you want to wait?
Is the PPT presentation available for everyone?
Sorry, all of these presentations will be available on the Cronus Chapter website, and also this is being recorded and there will be recordings.
So we do not need to take a picture or write down?
No,
Yeah.
all the slides will be on.
It'll be on the main Cronus website and the presentations.
Okay,
On the front page, somewhere obscure, there's a link.
super. Anything else? Yes?
Yeah.
You mentioned Windows and Linux. What about OS X?
So the deal with OS X, there is no announced plan by Apple to support Vulkan on OS X or on iOS. There is a Cronus member company called Brendel Workshop that is doing a shim layer, which will present the Vulkan API and backend on Metal. To the extent that it can, some of the capabilities aren't there. I have not used it. I know, and it's currently in development. But if you look for what's it called, metal VK? Is that what it's-
Molten now.
Molten VK. Or, yeah, sorry, I don't have it on the slides. I think it's molten VK. Anybody else? Sorry. Yes.
Quick technical one. Objects stroke resources shared across threads. So are those resources shared by anything on that device, instance device resources?
Right. So cross-device sharing is not in Vulkan 1.0.
Yep.
That is a high priority for us because we have lots of users who want to do big GPU farm things for film rendering, for example. And also there's the classic case of discrete plus embedded GPU. We want to support both of those. Currently, unfortunately, although you can create devices from two different physical GPUs, they're kind of in their own universes and you can't really do anything useful with them.
Understand.
Come. Yes?
Yeah, you said that you can't have two threads writing to a command buffer. Is that even if they're writing to different places of parts of the command buffer?
The command buffer you should think of as a tape recorder. When you place a command, it goes into the next empty space in the command buffer. So, okay. Michael, of course, is going to go into command buffers in much more detail. Yes?
What's the attitude to binary compatibility?
Could you repeat the question?
Sorry. The attitude for binary compatibility that is going forward.
Yeah, going forward.
Have we, somebody help me out here, you guys know the API better than I do.
Minor versions are backward compatible.
Right, yeah, right. So the intent is Vulkan 1.1 will be backward compatible, 2.0 might not be.
Implementation, but this is a good time to check the microphone. Is this
I
working?
can't hear you at all.
Can you hear me now? Is it working?
Yeah.
So even implementations that ship 2.0 will still continue to ship 1.0, so you'll still be able to create a older context on a user driver.
Okay. Yeah, there's a bunch of interesting issues that are going to come up when we decide we, for example, need to support multiple GPUs, and I have a 1.1 driver on this one and a 1.0 driver on that one. I assume the instance is how we're going to manage that. We haven't really mocked it up yet. Okay, yes?
From what I've seen so far, it looks similar to the way DX12 works. Has anybody done a layer that goes in either direction on top, like a shim layer?
Nobody's done it so far. Certainly, DX12 is conceptually very similar. There were some quite significant differences in state inheritance between command buffers, but other than that, they're pretty similar. I couldn't tell you, but my suspicion is that Mantle plays quite a role in designing DX12 as well as well. Okay, I'm going to say please welcome Michael Worcester from Imagination Technologies.
So,
all lines have been muted.
is this microphone working? Sounds like it's working. Is